servo motor is designed to move and then hold certain positions. Unlike traditional DC motors which constantly rotate, servos are designed to work with a certain range and stay there until they are moved again. Adjusting the angles helped us understand that robotic movement requires precision to complete tasks, and it highlighted just how crucial accuracy is in controlling positions. We noticed that even a small mistake in coding and wiring could make the servo motor unsteady or move at the wrong angle. At first, it was frustrating, but testing and adjusting the angles taught us patience.
Ultrasonic sensors measures distance by sending out sound waves and calculating how long it takes for the echo to return. In practice, it was fairly accurate, but sometimes the reading were a little off depending on the surface of the object or its angle. We noticed that factors like distance, angle, and obstacle could affect its readings, so testing and adjusting were important. Despite the small changes, the sensor allowed our system to interact with the environment. For example, it could detect objects and triggers the servo motor, or display the distance on the LCD. This showed us how sensors can make a system respond automatically.
The LCD showed distance values from the ultrasonic sensor and system messages. Feedback is essential in robotics to ensure the system is working and to assist users in understanding the system and to know if it's working correctly. Unlike normal LCDs that require many cables, the I2C model requires only 2 cables for data transfer. In addition to power, during debugging and demonstrations, the LCD was extremely helpful because we could immediately see whether the sensor readings and servo movements were correct, which made things fixing errors faster and the project more interactive.
System thinking emphasizes the relationships between things and how they interact as a whole. In our system, the ultrasonic sensor gave us the distance information as input. The sensor emits ultrasonic waves and calculates the time taken for the waves to return, which helps it determine the distance of the objects from the sensor. The servo motor serves as the mover, moving to certain angles depending on the output given. For instance, if the sensor detects an object, the rotation direction depends on the degree. The I2C LCD displayed the output, showing the exact distance reading from the sensor and a message indicating the current position of the servo motor, such as this 32 cm servo motor 75 degrees. This opened our eyes to automation. Automation is not merely a combination of different components functioning independently. Rather, it functions in a very smooth manner, which each component interacting with other components to form a self-regulating system. Each component relies on the information or actions of another component, creating a never-ending cycle of input, processing, action, and feedback. During our activity using the servo motor, LCD display, and ultrasonic sensor, the most challenging part was making all the components work correctly. At first, the servo motor wasn't responding properly, and the LCD sometimes showed the wrong distance.
There was also a time when the code and wiring were already correct but the system still wouldn't upload. We had to disassemble the wiring and put it back again and upload the code all over again. But instead of getting frustrated, we checked our wiring, reviewed the code line by line, and tested each component separately to find the problem. We also asked for help from group mates and asked help on our teacher to help us understand what's wrong with what we're doing. Through this process, we improved our patience, logical thinking, and our ability to do the tasks. More importantly, we learned how teamwork and careful debugging can turn mistakes into learning experiences.
The skill most our members found most valuable in this class is learning how sensors, motors, and displays work together as a system.
Writing code and connecting wires is one thing, but seeing everything respond in real time really showed us how automation works.
It taught us patience, careful observations, and logical thinking because even the small mistakes could affect the whole system.
And our advice to future students is to stay patient and test each part step by step.
Don't be afraid of mistakes. Figuring out why something isn't working is where the real learning happens.
You keep trying, you'll not only get the project to work but also understand how robotic systems come together, which makes the experiences really rewarding.
One key takeaway from our robotics class is that understanding how each component works together and how mistakes help us to improve our skills. Every mistakes in wiring and coding teaches us to be better solving problem. As we move forward, we will apply what we have learned to create more projects in the future.